All right, so this is title of this talk is Exodus and the Third Order. Um, and I'm going to tell you what that means here in a moment. But first, I want to talk about what we've been doing that's not Exodus related. We have been quite busy, Tim. Um, as you mentioned, we have been removing dust on the moon. This is something we've been doing for 25 years at NASA. So we just got our EDSs, our electrodynamic dust shields, operating on the lunar surface in March of this year on the Firefly lander, part of the Blue Ghost mission. So you can see that we can clean glass and thermal radiator surfaces free from dust on the lunar surface, which is very exciting. In addition to that, we're sending humans back to the moon and Mars, so that's been keeping me very, very busy. But the Exodus team is working on other technologies, not just propellantless propulsion.
Okay.
So Exodus has been busy. We've continued the development and experimentation on new class of thrusters. Drew will talk more about that. Ongoing experimental validation of the Exodus force by others. So this is a big one, Tim. Since the last we've talked, we were able to perform the Exodus effect in other vacuum chambers, so it's not a test setup issue. They were verified at other laboratories by other groups, which is absolutely necessary. There were even Exodus test articles that were built, developed, and tested at other locations. So this is how we get this theory into practice in the real world, is to have other researchers design these, test them, build them in their own chambers, their own facilities, and that has been started, which is outstanding. So this is really good news for us, for Exodus. We knew it would. We knew it would work. So we're not infinitely surprised by that, but it is exciting to see this actually happen in the last year or so. So that's been fantastic. So we always get the question, where does the force come from, right? The classical electrostatic pressure force and the divergence force, which we call the divine force, the divergence in electric field, doesn't adequately explain the generation of the forces. They're derived from the conservation of energy in the classical limit, but it doesn't really show you where the forces come from. So today we're going to try to tackle that. Okay, and so what do we know? We do know that we're dealing with a quantum mechanical effect. We know that from the experimental necessity of the fine structure constant, which is a purely quantum mechanical variable. We know we're in the low energy limits of quantum mechanics. We're not splitting atoms. We're not generating very high energies. We're not doing anything in the high energy limit. These are test articles and voltages that people have common access to. We truly believe that this phenomena can and should be explained within known physics. We don't think there's a need to invent something new, and I think that's a very important point. So usually what happens is, people come up to me or they send me things about research that they've done, and then 9 times out of 10, it's something that's completely new, completely revolutionary, completely, crazy, out of this world stuff. And I love getting that. I'm not going to lie, I do love getting that. But really just don't have the bandwidth to start from there. So what I've been hoping for is to have some physicist kind of try to help me explain this with known physics, because I think we have the tools already to do that. I don't think it's necessary to reinvent all of physics, especially for the last, 200 years and start from scratch. I don't think that's necessary. So as we move forward, we want to keep in mind that we're trying to stay within the bounds of known physics. And that's important because, there have been many outstanding researchers that have worked on this for several decades, even centuries. What else? Where do we start? So we know the force is fundamental, and that's important. It should be able to act on individual particles and not just large particles or large systems of particles. The electrostatic pressure force on a single particle, regardless of their sign of proximity from another. So we should be able to see this on just single particles. We don't need giant structures to see this. This should affect every particle. We do know that Coulomb's law should dominate, but it's entirely possible that a much weaker, higher order term plays a role in the observed forces that we see. So when we start thinking about weaker, higher order terms, that lends us right to perturbation theory, which has been used to describe the Coulomb law of interaction between two particles to the second order. So this is where we're going to begin. So to do this, we need quantum electrodynamics. So we have to talk about QED, and I apologize to the whole audience for talking about QED. It's not something that people want to hear about, but it's probably a necessary evil that we have to go there. And we'll explain why we do that. Perturbation theory, this is how it works. So essentially, some of the perturbation theories are on the orders of alpha. So alpha is the fine structure constant. It's this weird number in nature. It's 1 over 137 that keeps popping up. Do not ask me where it comes from. I'm not going to tell people I know where it comes from. But since we've seen that in our experiments, we think that we are dealing with a perturbation theory. Basically, you start with an unperturbed system of energy, you make a little change to it, quantum mechanics, and then you see what the new energy is, you find out the new states, and then you start again with the second order and going to the third, going to the fourth. This has been done for the Bohr energies of the hydrogen atom. You can see different orders of energy based on whether it's the actual Bohr energy itself, fine structure constant, Lamb shift, hyperfine, splitting it, and etc. So there are many examples of this in quantum mechanics, and perturbation theory really is probably the greatest discovery in all of quantum mechanics. Is all of the great discoveries have been done caused by perturbation theory, which is pretty exciting. So, but before we get to that, we're going to show you where we're starting from, and I think this is important because there are other forces that come from where we're beginning, our background. What is the background? And the background that we're all in, where we're starting, is the background of the infinite quantum vacuum fluctuations. So the vacuum fluctuations, what the heck are those? So essentially, we live in the sea of this infinite energy that are called quantum vacuum fluctuations. And energies are just defined by this h bar constant times omega. You don't have to know all of this stuff, but I'm keeping it here anyway for the users, Tim, so that when people can read this, they can go through later and they can fill in all the parts. What I really want to come across is the concepts. The math doesn't matter. The concepts are what's important. So for something as simple, not simple, but something, for example, as well known as the Casimir effect, how does that work? Well, what you're really doing is you have these fluctuations in 3 dimensions, and you constrict it in one of those 3 dimensions. So these Ks are basically wave numbers. They basically have units of 1 over length. And what that is how we characterize energies. We do it in 1 over length. The same way we use frequency to use sound. We use frequency to use sound. We don't use time domain to talk about sound. We use frequency, which is 1 over time. The same thing with K. It's 1 over space. So we have space and time. We have 1 over 1 over length is our K number. Makes things very, very easy for physicists. We don't have to deal with inverse space. We can use K right away. But so all we do here is we just do in Casimir effect, we just essentially take this integral, we turn this energy into an integral, and we just integrate it over all space. We can do that in the X and the Y, which are continuous, but if we have flat plates in the Z direction, we constrict them. And we know how to do that from quantum mechanics. We put in a series expansion. And when we do that, we have a difference in energy of the one that's not constricted minus the energy of the one that is constricted. So the process here is to find what is that change of energy. When you do that, take its derivative, and you got the force. Boom. So your process is actually that simple. Find out what is your background energy, make a little tweak to it, subtract them, then you got your force. That's how Casimir did it. Now, Casimir is subtracting states away from the vacuum. So he's constricting the actual number of states in the vacuum. We're not going to do that. We're going to add states. So I'll show you what we're going to do. So perturbation theory. How do we use it for our case? Well, I'm going to start from the very simplest case that we can think of. And that is the case where we have 2 electrostatic charges, Q1 and Q2, at some distance R1 and R2 away from the source. Now, To do this, we have to do, when we start adding charges, we add them into the background of, this is the hard thing to say. The hard thing to say is it's in the background of these quantum vacuum fluctuations, these states. So we're starting from zero. But the states are not actually at zero energy. There is some energy above that. So we have, instead of using a Hamiltonian and getting equations of motion, is what you do in classical mechanics, you start with a Hamiltonian and you operate on states to get an energy out of it. And that's what we're looking for. We're looking for the lowest energy state. And the first energy state I'll show in a minute has no consequence. It doesn't change anything. But if I take these two charges and I put them in the vacuum, how does that energy state change? Just by doing that simple thing. I'm bringing two particles, I bring them in. How does that change the energy state of the universe? And add it all up, see what you get. Well, people have done this. So what I'm going to go through is I'm going to go through this horrible math, but I'm not going to go through it in detail to show you how you can use second order perturbation theory to come up with Coulomb's law, reals, which is what everyone knows. So we have these basically two terms. Our change in energy is going to be this first order term. Now these quantum mechanics are a little weird. You have to read it from right to left. But you start from a zero state, you add your coupling term, and then you finish with your zero state. You figure out what that change of energy is. Oops. And then you have a second order term. You do it again, but this time you insert some additional states. And I'll show you what that is in a second. So what we have to do is we have to define a coupling. H0 is the free charges in the system, or the free fields in the system. In this case, it would be the free fields. That is basically the ground state of the universe. Now we add two charges, and how do those two charges interact with that? Well, they act through this coupling, this AJ. A is the vector for potential. This is a very strange thing. You don't have to memorize this. This has all the information of the quantized electric and magnetic fields in it. That's all you need to know. It is actually the quantum version of E fields and B fields. It's all there. Someone else did this math a long time ago. I'm not going to go through that. This is the four current density. Whenever we say four currents, we're talking space-time. You have one time dimension and three space dimensions, and that's how all quantum mechanics is written. So we have our two charges, and they're located at R1 and R2, and the other three dimensions are zero. So we have two static charges sitting there in time, not doing anything. So we just multiply these two together. We get this awful equation. And I kept the second order perturbation theory equation up here. And now we have to find out what all these little terms are. So you expand it out a little bit. And this is a really kind of a good graphic here. You start from zero, you go through the coupling, you get to a new state K. What does that mean? What it basically means, you have nothing. The coupling creates a virtual photon out of the vacuum, and it ends up in state K. If that new photon state K interacts on that coupling again, comes back down to zero, then that's a non-zero result. This is all I can tell you. So essentially, you have a zero state, you act on what is called the creation operator, and you get a state K. On this other one, you have a state K, and you act on the annihilation operator. You go back to state zero. So you start from zero, go up to K, K to zero. Boom. Those are the only non-zero matrix elements for this simple case. In second order, because these are very strange things called, they are called photons. They're actually called virtual photons or scalar photons. They have this selection rule where that product is -1. We'll talk more about that a little bit later. But you do all of that math, you come up with, you solve these equation, and you multiply these out, you get these four terms. You get a Q1 squared over 4 pi epsilon naught R1, Q2 squared over 4 pi epsilon naught R2, and then Q1, Q2 over 4 pi epsilon naught R1 minus R2. This first one is the self-energy of the electron. The second one is the self-energy of electron at position 2. And the third one is the Coulomb interaction, Coulomb energy between both of them. So you actually get Coulomb's law starting from this covariant form of quantum electrodynamics. It's a very difficult way to do it. There's no doubt about it. But it actually does give you the right answer. So This is what you're trying to find. This is the force or energy of interaction between two charges, if they repel or they attract. And it all stems from solving these equations, which are not the simplest in the world to solve because you have e to the I kr over k squared. They're very, just takes some calculus there to do that. But once you do, you get the well-known results of Coulomb's law. So I'm going to leave it to the reader to do all this because that's not critical. But what is critical is that when you see this e to the I kr, that is a wave that is leaving the system. And the e to the minus I kr is a wave coming into the system, entering the system. So Richard Feynman created a whole bunch of what they're called Feynman diagrams based on this. Now, the Feynman diagrams are just a way to stop writing massive amounts of equations to solve the scattering matrix. So we can just draw it first and then write the equation and then solve the equation after, instead of trying to figure out what the equation is by using his Feynman rules. So what I've done is I've just drawn a couple of these things and what they mean consequent, what are the consequences of these things? Oops. Oh boy. So what I have here is the self-interaction energy. So essentially you come along, these lines that are straight are electrons. They're just hopping along in time. And this e to the I kr1, if you can see that, that is something leaving, boop. And then e to the minus I kr comes back, boop. So it conserves momentum. So essentially every single point where there's a vertice, momentum is conserved. So you lose some momentum here, you gain it back here, and through time, in this axis, time is to the right, there's no change to the system at all. That's how you interpret the Coulomb self-energy. Now we have to note that none of these diagrams represent Cartesian coordinates, which basically means as I have particles come in, they interact and they come out. That's not on an XY plane. It's actually on a very strange spatial time plane. So for example, the Coulomb interaction, Q1, the particle comes in, it emits what's called a virtual photon. So the Q1 does that. Oop, geez, I keep typing that. And the second particle comes in and it captures this virtual photon at R2. So you have the R1 minus R2. So you have the outgoing wave here and the incoming wave here, and then they go about their businesses. So it's like, so two particles, when they perform this Coulomb interaction exchange, it's like two ice skaters holding a bowling ball. One ice skater throws the bowling ball. The other ice skater catches the bowling ball. They slide on the ice, but they conserve momentum. The total momentum is conserved for the system, but they do this through a virtual photon. So in physics, all of the interactions that we are interested in, whether it's bosons, leptons, muons, kaons, every particles go through different interaction physics. The ones that deal with the virtual photon we call quantum electrodynamics, which kind of encompasses most of the particles that we're used to in everyday life. When you go to higher energy physics and you're talking about ripping apart protons from the nucleus or that kind of strong interaction, those are different particles and they would have different physics. But for the lower energy scale, particles interacting with charges and fields and so on, the virtual photon is the mediating particle. Now, it's not a real particle. You can't find it. You can't look for it in nature. But mathematically, it looks exactly like a photon. It has a couple of differences, though. It has, oh gosh, keep doing that. The virtual photon does have energy, has momentum, but it doesn't have spin, so it's not a real photon. But it is mathematically very similar to one. And that's how we explain interaction between charges. And when they did this years ago, 50 years ago, whenever they performed this interaction, they realized it was an exact solution. So it explains everything that we know about two particles. When two particles exchange charge, they can either attract or repel, and that's it. There's nothing else two particles can do. So why go further? I haven't seen anyone go further than that. There was no reason to. It's not just an appropriate, an approximate solution. It's actually an exact solution. So why would you go further? There physics out there to suggest that you needed to go further. There was no other phenomena observed until now. So now, with the Exodus effect, we are showing you that if you have two particles, there can be a net translation of both of them in the same direction. A force, if you will, from somewhere. So that's why we decided to go further. What are the higher order terms that are lower in energy? What are they? We think they play a role in what we're seeing experimentally with the Exodus force. So we went on to the third order perturbation. So for this, you start from zero, you go to state K, you go from K to K prime to K prime again. You sample all of that space, and you go on and you try to figure out what is your lowest energy in that case. So for the first order, this is basically your magnitude, roughly, of your coupling. The second order is magnitude coupling that we just did, and the third order magnitude coupling right here. Each one of them is increased, or decreased, I should say, by a square root of alpha. Alpha is 1 over 137, so you're losing about 0.08 in magnitude. So it's a square root of 137, which is 0.08. So it is getting weaker, much weaker in these higher order terms, but there's reasons to do this. Okay. So unfortunately, when you do the math, you get this awful nightmare, which I'm not going to read off to you. It is awful. So instead of 4 terms, you now have 12 terms. And we're going to explain what these terms are, but we're going to do it graphically. So you have single charge terms. These is force proportional to essentially Q1. It's cubed now, and it emits a virtual photon. Q1 can also absorb one, which didn't happen before. Q2, Q3 can emit one. Q2 cubed can also capture one. That was not available before. So we're going to talk a little bit more about that. We also get the same coupling-like terms that we did in the second order perturbation theory, where a virtual photon is emitted by one of them and captured by the other. That still happens. There is a higher order term in which one of the Q's is squared. Instead of Q1, Q2, you have Q1 squared, Q2, Q1, Q2 squared. So you have, these are smaller in value because Q is a small number. Squaring it makes it even smaller. But we still have 4 of those terms. The interesting ones, though, I think, are the coupling terms, where we are mixing the Q's with the photons that are being emitted. Because when one emits, the other one goes to the new momentum too, but it doesn't actually get captured by the photon, the virtual photon that the other one emitted. So in this example, I draw Q1 emitting one. The R1 tells you that the Q1 emitted that one. Q2 just doesn't do anything. It just follows along with the momentum of Q1 because they're physically attached. The same thing here with Q2, Q1, 2, and Q2. You are coming along. Q2 all of a sudden emits, doesn't emit, but it interacts at R2. It escapes the system, but the entire system together has a momentum exchange. Same thing with Q1, Q2 squared, incoming from R1. So Q2 is getting incoming from R1. And the same thing over here from R2. So you got incoming and outcoming momentum. What are these momentum? Now, in QED, if you have enough energy, you are actually dealing with real photons. So if you're dealing with Bremsstrahlung, Compton scattering, Raman, you are actually dealing with real photons. But these are the scalar photons, the virtual photons, but they're not real. So what are they? Well, there's a couple of contenders. Most likely, though, they're probably just the external field. So in QED, when you have an external field, it's kind of looks like this. So you have a charge coming in, has momentum P1, and then it comes out with a momentum P2, and it can interact with an external field, which is drawn by this X. So an external field can come in here with this, looks like a photon, very similar to a photon, with momentum K, and K is actually the actual difference of both of those momentums. And the form for this Feynman diagram is very similar to the form we already have for our scalar photons. So it's most likely, my bet would be that these are just simply the quantized electric fields. One thing that's nice about that is this tells us that electric fields possess momentum, even on the quantum scale. So we don't think about electric fields possessing momentum, but we do know classically static electric and magnetic fields do possess momentum, even at zero frequency. So we can get momentum in fields. We also can get momentum in quantized electric fields and magnetic fields. So that's where you're getting momentum from. And these quantized fields come from the vacuum. So in third order perturbation theory for our Exodus pressure force that we see, if we have a charged plate here on one side, and say we have a positive or negative E field to the left of it, let's say it's being generated by whatever charges are in there. So in this example on the left, we have Q1, Q2. In this case, we have Q1 emitting or capturing an incoming virtual field, I guess it would be called now. The same thing with all these other charges that are happening here. They can absolutely get momentum coming in to hit these charges. That's what these terms are. The same terms on that left side where the field is, they can also emit and talk to the field that it came from. So these are also emitting field on the left side of the plate. In both cases, the force is to the right. So wherever you have a non-zero, I guess you would say these electric field amplitudes, quantized amplitudes, you would have a force in the opposite direction. The momentum would go the other way. So you have a recoil, if you will. It's a quantum mechanical one, but it's there. And that's how we would explain our electrostatic pressure force. So if we make a field and we make sure that it acts on charges, all we have to do is make sure that we have the field in a location where it's asymmetrical. And we can easily do that. So I just want to remind you, we haven't done all the math completely, but our charge we get from Gauss's law, epsilon naught EA, Q squared is epsilon naught squared, E squared, A squared. Pressure is epsilon naught E squared. So the electrostatic pressure is the square of the field times epsilon naught, and our force is that times the area. So that's how we get the classical versions of our forces. But quantum mechanically, what's actually happening is these interaction terms from these quantized fields are the ones doing, transferring all the momentum. They're the ones doing the work. So final notes here. The energy of the system that we found is lower than the second order by a factor of square root of alpha. We knew it would have some proportion to alpha. It was kind of interesting that it's square root of alpha, and it turns out that that kind of matches the number of charges. So for each order, you have an interaction charge. So you have first order is 1 charge, second order is 2 charges, third order is 3 charges. Every time you add an order, you add a square root of alpha. The selection rules, this is very exciting, for the creation and annihilation operators is now +1 and not -1, as it is in the second order. What the heck does that mean? What that means is you put a ton of energy in there to get your 2 charges in this system. So your energy is way above the vacuum energy as it was when you started. But now, because you're looking at the third order is energetically favorable because it has a negative component to it. So basically, you're coming out from zero, you're putting in your square root of alpha energy in there with your 2 charges, and even Q's, which we haven't talked about. You're putting in your charge energy in there, your Coulomb force, whether it's attractive or repulsive, it's there, it's very strong. And then you also have this other component that's a little weaker, but it's there, and it's a little negative. So your system will try to find ways to get to lower energies. The third order allows you to get to a lower energy state. So systems will naturally want to get there. This might be a way for them to do that. The fourth order doesn't show anything new. I've done the math for that. It's horrible. Don't recommend it. But it does show the same things as the second order, where you have particles coming in, they're captured by the first particles. So the momentums are all encased. There's nothing leaving the system. So there's nothing new with the fourth order. There's a lot more to go. We have to solve this equation. So when we do the graphical terms, this is what we have to integrate them over. It wasn't nice like it was in the second order, where it was just 1 over k squared. If it was, this would be just 1 over r, and we would be done. But it's not. It's 1 over k to the 7 halves, and it's this mess, which is a gamma function, and it's horrible, and I don't recommend it for anyone. So if you really want to torture yourself, you can try to figure this out. I had my students on it; they did not enjoy it. So, but that's something that has to be done in the next few months or something. Then we have to compare the results to the thousands of experiments that Drew has been doing, because we have a lot better resolution now on the physics, and on the math we got to compare. That's going to take a lot of time, and then once we do that, we write up a paper. So that is where I am at, Tim, for theory.
Wonderful. Charlie, thank you so much